Okay, so this question comes from June 2006 and it's from Module 6, question 2, and it's on nuclear fusion. And the interesting thing here, in June 2004 they asked for an equation which gave an equation for the fusion reaction for hydrogen, and so there's a good example, and it's probably worth learning that equation for future reference. But here we're given some data and we're asked to use the data to calculate the energy released in this reaction, and obviously it's a fusion reaction. So what we're seeing here then is, here's the nuclear masses. So what we're going to say is that the energy release, so that's delta E, is equal to then delta M times c squared, where delta M would be the mass in kilograms and c is the speed of light. So we need to then take these masses here and we're trying to work out delta M from the equation up above. Right? So what that means then is that delta M, if we look then, delta M is equal to, well, the equation tells us hydrogen, a hydrogen 2, which is deuterium plus tritium. So we're looking for deuterium and tritium, so that's equal to, if we look there, deuterium and tritium, that's going to be 2.014102 plus 3.016030, and we're going to subtract from that then the right hand side of the equation, which is the helium and the neutron. So that's going to be 4.002604 plus 1.008665, and when you subtract those two, what we find is that delta M is equal to, and when you add those up and subtract them, you get that that's equal to 0.01883 mass units. So that's delta M in mass units. We need to convert that then into kilograms, so that becomes equal to 0.018663 times, and the conversion, if you look on your formula sheet, is 1.66 times 10 to the minus 27, which turns out to be, whenever we calculate that, turns out to be 2.82 times 10 to the minus 12 joules. Right, so when we put in E equals mc squared, that's how much energy that we find, and so that gives us a value of 2.82 times 10 to the minus 12 joules. Next question then is a reverse of the previous question in 2004, where in that we were asked to work out the temperature. Here we're asked to work out the kinetic energy of a particle. So again, what we're going to say here is that the kinetic energy of the particle is equal to 3 over 2 times K times T. So that's equal to 3 over 2 times, and K is 1.38 times 10 to the minus 23, times the temperature, which is 8.0 times 10 to the power of 8 Kelvin. And if you remember from the last one, we had something times 10 to the 8 Kelvin. So again, the temperature for fusion is up and around that 10 to the power of 8. And multiply that all out, and that gives 1.7 times 10 to the minus 14 joules. So that gives us our answer, that the kinetic energy of the plasma, of the particles in the plasma, is approximately equal to 1.7 times 10 to the minus 14, and it's an approximation because we're assuming that it behaves in the same way that the molecules in a gas behave, and that its kinetic energy is 3 over 2 kT.